So Paul, you can see that the distance ladder is a little complicated, and we have this nasty stuff like dust that is spread through the cosmos, causing us problems.
Oh, dust isn't nasty. Dust is really pretty. I mean, just look at images like this taken at the Anglo-Australian telescope. What you're seeing here is stars, and these dark patches here, it's not gaps in the stars, it's dust clouds, interstellar dust clouds blocking the light from the background things. This is just gorgeous. You can even see it with the naked eye. Here's a picture I took of the 74-inch telescope at Mount Stromlo, with showing the centre of the Milky Way in the background. And what you can see up here is the dark bits, the dark lanes in the middle of the Milky Way, which is where the dust is blocking the stars. But also off to the side, you can see it's got a somewhat reddish colour here. And that's where there's not the really thick dust, but there's a little bit of thin dust that's blocking some of the light. Now this is just really pretty. You can see it in other galaxies as well, and once again it makes things gorgeous. The sort of spiral pattern you're seeing here is not actually where the stars are. The stars are actually pretty uniformly distributed. The spiral pattern is mostly due to dust blocking out certain areas and making it all look so gorgeous. So how can anyone not like dust? It's just so gorgeous.
Pretty it might be, Paul, but unfortunately, in terms of what I like to do, which is to measure distances, dust is everywhere. And the fact that it helped create the Earth is no solace to me when I try to measure the distance to this galaxy. So this galaxy, for example, is full of Cepheids. The Cepheid variable stars are scattered around it, but most of them end up landing with some amount of dust unknown in front of them. And that means when I try to measure the distance, I get too far of a distance whenever there's dust in front of it, and I get about the right answer when there isn't.
And you have to bear in mind, you see, for example, really strong dust here, but there's probably dust there and there and there as well. It's just a bit fainter. But almost every line of sight through almost any spiral galaxy is going to go through at least some dust. There are no real dust-free
That's
views.
right. Only if they're way up on the top side, you're sort of out of the plane of the galaxy. And, you know, these big dark areas we don't worry too much about because there's so much dust there, you just can't even find the stars there. So that's not the problem. It's the insidious stuff that's everywhere. It's like, well, it's like the dust around your house. It's always there and nothing you can do to get rid of it.
Well, interstellar dust is actually not very much like the dust around your house. I mean, the dust around your house is actually mostly flaked off skins of human skin, which is definitely not the major contributor to interstellar dust. In fact, it's probably more like smoke on Earth. The particles are very much smaller than dust. You couldn't see them with the naked eye. They're probably microns or even nanometers across in size. Yep. Very tiny grains. And this means, because they're so small, they're comparable in size to the wavelength of light very often, and so they have a really strong effect on things about the same size as they are. Which typically means blue light, whereas they have less and less effects at longer and longer wavelengths. So what we're doing here is I'm plotting the wavelengths, starting with very blue and going out to, say, the infrared, and we're plotting what fraction of light can get through a cloud of dust. Now if you have a thin cloud of interstellar dust, it'll look something like this curve over here. So the infrared light mostly gets through, might be 99% of it's getting through, but as you get to shorter and shorter wavelengths, the fraction getting through gets less and less and less. And so you're losing maybe 40% of the light in the blue. Now if you ramp up the amount of dust and have more, it might go something like the second curve. In the infrared you're now losing 2%, but by the time you're down here in the green or the blue you're losing nearly all the light. And if you add even more dust it gets worse still, but it gets worse primarily the blue. So this, it occurs, gives us a way to find out how bad the dust is and to correct for it. So what you could do is, instead of just taking a picture at one wavelength, you could say pick two wavelengths, say a blue and a red wavelength. And you measure how bright your Cepheid variables or your supernovae or whatever they are at these two wavelengths. Now you have to know what colour they are if there's no dust. You probably just take the bluest thing you can find and treat that as if it's got no dust. It probably still has small amounts of dust, but you can maybe ignore that. And then for another one you can say, well, let's say it's down at 10% in the blue compared to the red. That probably means it's on this curve. Whereas if it's down by twice as much in the blue and the red, it's probably this curve. And if it's down 90 times as much in the blue as the red, it might be that curve. So by looking at two colours and seeing, you don't know how much it's down in either, but you can look at the ratio. And if it's a very big ratio of red to blue, that means there's a lot of dust going on. It looks red to the eye and to the telescope. So surely you can just measure the colour and say, well, that one looks very red, therefore it must be on this curve, and that will then read off from the curve how much of a correction to make and how bright it really should be.
Oh, Paul, if only things were so easy. So there's a number of problems. The first problem is, let's just take Cepheid variable stars, our venerable tool for measuring distances. It turns out that Cepheid variable stars have a range of colors. So when I do this ratio, I don't know what to compare it to. Is it the blue part of the Cepheid or the red part? So that means I'm going to have uncertainty when I apply it to a given Cepheid. But that's just the beginning problem. So a type 1a supernova, for example, I could try to use it. Now, the type 1a supernovae are pretty well behaved, we think, in their color, although probably not perfectly. But then we look and not all dust is the same. You plotted these curves like they're the only ones. But in fact, there can be different dust laws because the dust has different sizes. And we see this with the type 1a supernovae all the time. There seems to be bigger dust and littler dust, and we don't know which it is unless we get huge amounts of data, which is just simply not practical in most cases.
Yeah, so here I've got two different dust extinction curves, and they both have the same ratio of red to blue, but they're actually quite different amounts of absorption. One's twice as absorbed as the other. And we know this is a problem. I mean, this is actually some work I do, because I like dust. I've been actually trying to measure properties of dust in distant quasars, and you can find, particularly at blue and ultraviolet wavelengths, there are all sorts of features. The dust is probably produced in winds of red giant stars mostly, but then some of it is destroyed, particularly if there's hard radiation like a supernova or quasars nearby that can destroy some of the dust grains and leave other ones. There can be chemical reactions that change them, catalysis on the surface. The dust can be really complicated, and for different sorts of dust properties and different ratios of big dust to small dust, you can get very different curves. So this colour method may work as an average, but it's not that great.
It's true. So, you know, the obvious thing to do is just not to work here, but to work over here, where the effects are much smaller.
And indeed, here's an optical picture of galaxy NGC 253, and you can see very broken up by dust. If you look at the same thing out at the wavelength of 2 microns in the near infrared from the 2 micron all sky survey,
it's almost a completely different looking galaxy. And you can see the stars are the same, so it gives it away, but yeah, all those stars has a big bar across the thing. It looks completely different.
There's still a bit of dust you can see in here, but it's got very much better. So working at the infrared works well. I mean, some work I did, this is a what's called a blob, a giant forming cloud of gas in the early universe, blob 6 this one is. If you look at the optical, you don't see very much. At the infrared, it's a whopping great collection of massively star-forming galaxies, which you wouldn't even see in this over here. So it makes a huge difference going out to the infrared.
So the infrared is clearly where we want to work. The problem is observing in infrared is really, really hard from the ground. It requires to do accurately very big telescopes, very good sights, and it turns out that our detectors are really problematic in the infrared.
Yes, we normally use charge-coupled devices, which are silicon chips, the same as you've probably got in your cell phone or digital camera. The trouble is, silicon has a band gap energy that corresponds to a photon with a wavelength of about 1.1 microns. What that means is to detect any light falling on it, the photon has to have enough energy to knock an electron away from its lattice position.
Yep.
And anything in the infrared can't do that.
Yep, they just sort of go right through the silicon. It's transparent, effectively.
So you start needing to use exotic semiconductors. So instead of silicon, which you can pick up on any beach, you start using like indium antimonide or mercury cadmium telluride. And that puts the price through the roof. A, because the elements are rare and expensive, but secondly, because they're not being manufactured in millions for camera phones all over the place. It's very complicated, difficult manufacturing process, which puts the price through the roof.
And the other problem is these same detectors are used by the defense industry, which means it's actually really hard to even get them at all because they're considered to be top secret.
So many countries are not allowed to import these things at all because of the military export rules. But even if you've got these wonderful detectors, then you've still got a problem in that at most infrared wavelengths, you're close to the wavelengths at which the black body of the Earth temperature emits.
Yep.
So trying to work at, say, 5 micron wavelength, your telescope is going to be glowing, because at 5 microns, you and I and the telescope and the dust in the Earth's atmosphere are all glowing like crazy. So it's like trying to work in a dome with the lights on and the telescope made of fluorescent tubes.
Yep, so you have that background problem, and then you have another problem, which is the diffraction of light. When you're working in the infrared, the telescope is closer to the wavelength of light, and so your resolution shrinks down. So when you want to look at something like a Cepheid, normally, if you're looking at it in the blue light, you can see it because it's a nice sharp image. When you look at the infrared, it's blurry. So all these things make it really hard to observe in the infrared.